and he's a postdoc from Berkeley. And then he joined the faculty of TIFR in 2012. So, and he has been there since and working on superconducting qubits. He has been working extensively, and he's one of the known faces in the country on quantum information, experimental quantum information. And he has got a lot of projects also, grants also. So Vijay has published quite a bit of papers even after joining TIFR. So I'll just hand over the floor to Vijay. So today he's going to present what he has been doing in TIFR since. Vijay.
Thanks a lot for the kind introduction, Chiranjeev, and thanks to the organizers, Prashanta and others, for inviting me to this summer school in IISER Kolkata. I will, in this talk, introduce you to the field of superconducting quantum circuits, which is currently one of the leading candidates for a platform where a practical quantum computer might be realized in the future. I'm sure most of you are aware of the developments around the world, and there's a lot of news these days about these things, and many of you are probably already using some of the present day, what I like to call toy quantum computers by accessing them online. We've also been trying to build some of them at a smaller scale in our lab, and towards the end of my talk, I will tell you a little bit about the kind of projects we are doing. But in most of the talks, I will essentially introduce you to the idea of how superconducting electrical circuits can actually behave like quantum objects and how one can use them for quantum information processing. Chiranjeev, just a quick question regarding the question answer.
Yeah, so there will be a question answer session at the end. But if you can say if somebody has a pressing question, that person can just unmute.
Yeah, I think it's best that we periodically pause and check, and if there are questions in the chat, I can periodically.
Right. So you can fine then. So in order to see the chat, you have to pause, right? So fine.
Yeah, I think some kind of pop-up shows up, but let me see.
Yeah, pop-up. It's actually a little bit disturbing. I'm sorry. People do. Yeah, you can proceed. Yeah.
Okay. Is my slide visible now?
Yes, it is visible.
Yes. Okay. All right. Great. So let's get started. And I mean, you have been attending this summer school for a couple of weeks now, and you've probably been introduced to the general idea of what quantum information processing is, or more particularly quantum computing. This slide essentially summarizes, if you want to say in a very simplistic terms, what one needs in order to build a system which can carry out these kind of quantum processes. Give me just 1 second. I'm having some audio issues here. Just be. Okay, hopefully it's better now. All right, yeah. So the sort of the essential elements of what is required for building a quantum system. The first most crucial element is that you need some physical quantum two-level system. Here, there's sort of a cartoon version of electronic state, say in an atom. That's a valid choice. Depending on which atom, it might not be the most practical choice. But you need some physical system where these quantum states can be encoded. You then need the ability to change these states and put them in the state you would like them. So you need a very good ability to control and manipulate them so that you can create arbitrary states like different kinds of superposition states when it comes to, say, just single qubits. You also need the ability to measure the quantum state very precisely. Now, depending on the kind of processor architecture, this measurement might only happen right at the end of the algorithm, which is sort of the situation today for most processors. And basically nothing else happens after the measurement. It's the last step in your execution of the algorithm. But as I'm sure some of you know, that there is this thing called quantum error correction, which is very important and crucial for really building a practical quantum computer. And there the measurements play a key role in actually identifying errors and then fixing them. And so these measurements have to be very, very precise. And this might sound like a very trivial requirement, but it took decades of, or maybe at least a decade of work to really get this to work properly. These quantum systems are extremely fragile, and making high quality measurements on them was not a trivial task. In fact, some of the works done on trapped ions in the 80s led to the Nobel Prize in 2012. So it's a very important part of the scheme of things here. And then finally, just having single qubits is not enough. A powerful quantum processor will require many, many qubits. And it turns out that you at least need the ability to create interaction between pairs of qubits, right? And this really means that there has to be some kind of a physical interaction between these objects which are storing the quantum states. And that combined evolution of a multi-qubit system, or at least a 2-qubit system, is what we refer to as logic gates in the quantum computing era. In the quantum computing framework, as compared to logic gates in classical logic, like AND gates and NAND gates, so where you have multiple inputs coming in, and then there's some operation and an output which depends on the input states. Similarly, in quantum, just to sort of parallel it with classical logic, we call them gates. But unlike classical logic, it's not, the signals are not necessarily traveling along a wire and reaching some object and the gate is being operated. Instead, the quantum system itself is changing. It's the evolution, the combined evolution of a multi-qubit system or a multi-component quantum system, which can be described as logic gates. I'm sure you know that these are essentially unitary operations on these quantum systems. So the qubits themselves evolve from some initial state to some final states. And these coupled qubits, coupled evolutions is needed to be able to create entangled states, which are an important class of states that have to be created to do anything useful with the quantum processor. And these are the basic building blocks. And the sort of the two main things, one is fighting against the main challenges, if I could really simplify it, is really the fact that there is finite quantum coherence, which essentially means that these qubits are not stable. You prepare in them some state, and one of the simplest things that can happen is that they just decay back to the ground state, because all systems tend to do that. And that's, from the point of view of computing, is a terrible, terrible thing to happen. It's like all the data just got erased in a very short period of time. So one is constantly fighting that, and this time scale can be very small depending on the physical system or large. And there's been a lot of work on improving this number. And then, as I mentioned earlier, quantum error correction ultimately will even allow you to use such unstable systems to actually make practical quantum processes. And then really to get all of these to work as you go to larger and larger number of qubits. This again, it's not a trivial thing to just go from a few qubits to a very large number of qubits. There are lots of engineering challenges, but things are moving along, and that we now have chips with 50 qubits or maybe even larger around in the world these days. Okay. So this is sort of, in a nutshell, what we need to build a hardware system capable of implementing these quantum operations you might have been studying. Okay. And this physical system can be of many types. There are a few examples shown here. As I mentioned earlier, experiments in trapped ions led to the the Nobel Prize in 2012. And what you're seeing here are just pictures of two ions which are suspended in vacuum with the help of electromagnetic fleets, and they are fluorescing. So you shine laser light on them and they re-emit the light. That's the picture shown here. And that is one way of building qubits. You choose some appropriate electronic energy levels which are long-lived, easy to manipulate, and so on and so forth. And you use lasers to manipulate and measure them. Similarly, you can also confine a single electron on a two-dimensional electron gas, and these systems are called quantum dots. This is again sort of a cartoonish picture. There are all these electrodes which help confine the electron cloud so that you effectively have one effective electron in that small region, sort of the dot region. And then because electrons have a spin, you can then apply a magnetic field, and then the spin can take either can point along the magnetic field or opposite to the magnetic field, giving rise to two energy states. And these two states can be used as your qubits. So essentially spin up and spin down. The common feature between these first two examples is that these are microscopic systems. These are individual atoms and ions, and this is like a single electron effectively being confined. And in contrast to that, we have the superconducting circuit, which is a picture is shown here of a part of a superconducting circuit. This is called a squid. There are two Joule junctions at these two regions, and this material is aluminum on a silicon substrate. And the size scale here, this with square-like thing, is about 5 microns on one edge. So it's much, much bigger than the trapped ions or the quantum dot system. If you can, it's not really an isolated electron, but still it's a microscopic degree of freedom. And here you actually have a much bigger object, and yet under the right circumstances, this object can show quantum mechanical properties. And I'm emphasizing this is because this was not really obvious a few decades ago that largish objects can show quantum mechanical effects. But this is now one of the most successful quantum platforms, and we will see how that quantum properties emerge as one goes along to look at these circuits, right? And of course, there are many others one can make with photons, cold atoms. There are topological qubits or nitrogen centers in diamond. And all of them, you carefully choose the two levels you would like to work with. And there are lots of pros and cons. And it's still a fairly open game, even though superconducting circuit and trapped ions are currently leading the race, with quantum dots maybe sort of a close third, I would say. There are many new results which shows that maybe with photons one can actually build, and maybe tomorrow there will be a completely new hardware platform which really solves all the problems, and that could lead to the first practical quantum computer. We really don't know, and so it's sort of both frustrating and exciting at the same time from that perspective, that we still are exploring many options to build this. And you never know that it could also be a combination of many of these ideas together to make a quantum processor. Okay, so what we will be focusing on today is the superconducting circuit. Like, how does one think about it in terms of quantum effects? How does one build these things? What are the right conditions under which one needs to operate them? Right? So really, to go back to think about even electrical circuits in the quantum domain, we just have to consider a very simple electrical circuit, which is just an inductor and a capacitor in parallel, just an LC oscillator. I'm sure many of you have done these experiments in your undergraduate lab. The resonant frequency is given by 1/square root of LC, but we don't really do any quantum mechanics in our undergraduate labs. But this is essentially a harmonic oscillator. You can write down the equations of motion, and when you study quantum harmonic oscillator in your introductory quantum mechanics class, you don't often mention what the oscillator actually is, right? We just write down the Hamiltonian, or we start with the equations of motions and then we write down the Hamiltonian. We don't often think about what is the physical system this oscillator is referring to. Most commonly, one would imagine a mechanical system, maybe a mass spring system, which is a common thing in mind. But if you actually look at the equations of any harmonic oscillator, it's the same, right? You might have some other quantity might be oscillating, but there's always something equivalent to a mass spring system. There's some stiffness constant or a spring constant. There's a mass term, and so on and so forth. So similarly, one can actually see that an electrical LC oscillator has exactly the same equations, and hence, if one were to just quantize it and write down a Hamiltonian, has exactly the same Hamiltonian as any quantum oscillator. And this means that I can think about this oscillator as a parabolic potential with equally spaced levels, which is what we learn about for a quantum harmonic oscillator, right? But the key points are, what is this energy difference, h bar omega? So we'll come to that in just a second. It is possible to write down the Hamiltonian or the equations of motions in now terms of the charge on the capacitor or the flux through the inductor. And it turns out that these play the role of position and momentum. The flux being like the position and the charge being like the momentum. And similarly, they obey the commutation relations which position and momentum operators do for a quantum harmonic oscillator. And just to show you that this flux and charge are related to the commonly used electrical quantities, currents and voltages in the usual way we understand them, right? That's flux is just inductance times the current, and the charge is capacitance into the voltage. So this sort of connects you to from the macroscopic degrees of freedom, like the current and the voltage, to the charge and the flux, which can then be thought of now as operators, really, and one can make a quantum mechanical treatment. Okay, so all of this is, of course, just mathematical jugglery. What does it have to do with a real experiments, since you have looked at these objects in your lab and never really looked at any quantum mechanical effects? The problem really comes about is in getting the right operating conditions and the right regime for the parameters. And the most important parameter here is this energy scale so just basically the difference of energy between the ground state and the first excited state, right? Typically, if you now calculate this energy h bar omega for the kind of oscillators you build in your lab, in your undergraduate lab, the frequency is going to be in kilohertz. And this h bar omega is a tiny, tiny, tiny number, right? Because the Planck's constant is extremely small. And if you compare that with the thermal energy, you're going to be in a regime where the thermal energy is much, much higher than h bar omega, right? Which means for the typical kilohertz oscillators, the ambient energy in the environment, or even of the objects itself, the inductors and the capacitors, is so much higher that the idea of just talking about two levels is just completely nonsensical. You have millions of levels being involved because you're at a much, much higher excited state compared to the ground state of that oscillator. So this is one of the main reasons why you don't see any quantum mechanical effects in a LC oscillator in your usual lab. So in order to be able to see it, one of the first things you have to do is to go to extremely low temperatures so that this condition is satisfied. So the thermal energy is now much smaller than h bar omega. So you reduce the temperature, but also to help you, because you don't want to, if you actually calculate the effective temperature for kilohertz, it will be in some microkelvin or maybe even nanokelvin range. Those are very small temperatures, difficult to achieve for bulk objects like an oscillator. So you increase the frequency of the oscillator to somewhere around 5 gigahertz. This is microwave frequency regime. That in temperature units is about 250 millikelvin. And then an operating temperature of 10 millikelvin is sufficient to achieve this condition so that you're deep in the quantum regime. And this 10 millikelvin is not a magic number. It just comes from typical instruments which are used to cool these down. That's called a dilution refrigerator. And they typically have a temperature range in the 5 to 10 millikelvin. Okay, so that's where this comes from. So as long as you're now sufficiently above it, you are conveniently, in this regime. And now you can really expect that if you leave the oscillator, you're going to be not populating any of the higher excited levels. You're always going to be in the quantum ground state. Okay, so this is one very important factor. The second is also equally important is dissipation, right? If you just take a pendulum, which is like an oscillator, and you set it oscillating, after a few seconds, it stops. Why does it stop? Because there is friction. The energy you put into the oscillator was dissipated away because of the friction, and then it stopped. The quantum mechanical equivalent of that is you put the system in the excited state, and then it decays back to the ground state because of dissipation. In the electrical context, that dissipation can be modeled as a resistor, say in parallel with these circuits. And if you have dissipation, you're going to cause the system to stop oscillating, which in the quantum picture means that it'll come back to the ground state. This is the decoherence I was mentioning. And sort of a cartoonish way of saying that these levels are no longer sharp, they are broadened because of this dissipation. And when you measure resonance curves in your lab, you see that the resonance peak has a width to it, which is related to the dissipation. So typically, if the width is so large compared to the spacing, you're not going to see a quantized effects, right? That's what happens again for typical oscillators in your regular lab. So you need to use extremely low loss systems so that the dissipation is minimized, and electrically, which means you have to use superconductors. So that is where the superconductivity comes in. It allows you to build oscillators which are extremely low loss. Okay, so that's the second key requirement. So you need to build low loss oscillators, and you have to go to very low temperatures so that you are in this regime. And for that, you need superconductors. And because you're at low enough temperatures, you will have metals which will become superconducting in this regime. For superconducting qubits, typically the material which is used is aluminum, though new materials are constantly being explored, with tantalum being a latest addition. And aluminum becomes superconducting at about 1 Kelvin. So this is well below 1 Kelvin. So you are nice and superconducting. Okay, so these two are important aspects. Now, there is a slight problem with the quantum harmonic oscillator. And it's this fact that all these energy levels are equally spaced. Okay. And typically, the way you excite this resonance system is by sending in a forcing term, which in this case will be a microwave radiation, which is in resonance with this transition. But because all the other transitions are also resonant, you will actually keep climbing this ladder, right? And you will not be confined to the two lowest levels, which is what you need to build a quantum two-level system or a qubit. So this doesn't work out, even though, and this is something I'm not going to discuss in detail, there's a lot of new work on using quantum harmonic oscillators as well. But you need a second object to be able to prepare the state of these systems. And that object also needs to have the important property, which is that of nonlinearity. This is a harmonic oscillator. It's a linear system. There is no nonlinearity, and the levels are equally spaced. And for that, we need to consider this very special device called the Joule junction. It is sort of the building block, most important building block of superconducting quantum circuits. You can really think of this as the transistor equivalent for classical chips. And this provides all the nonlinearity. Okay, the Joule junction is basically two superconductors separated by an insulating layer, and its symbol is a cross. And it has a current and voltage relationship. Brian Josephson, the inventor of this device, he wrote down these equations and was awarded the Nobel Prize for discovering the Josephson effect, which basically says that even though there is an insulator, electrons can tunnel and give you a dissipation-free current transport, which means a current without any voltage developing across it, which you expect for a normal superconductor. But this is a tunnel barrier because there is an insulating barrier. But even if the tunnel barrier is thin enough, this effect takes place. But that introduces some interesting properties, which is shown here. This current is proportional to the sign of this quantity delta. Okay. Now, for those who know superconductivity, this delta, you can think of that as the phase difference between the macroscopic wave function defining the superconducting phase on one side to the other side. If you don't know that, that's fine. Alternatively, you can really think of this delta in terms of this second equation here. It's really like a flux. It's the derivative of this quantity is related to the voltage. So we know that voltage is proportional to the derivative of flux with time, right? d phi dt, Faraday's law. It's essentially the same thing, just renormalized with some coefficients here. So the two are equal. So really, that is in fact this delta is called the gauge invariant phase, and it's defined as the inverse of this equation. It's the time integral of the voltage with respect to time across two terminals, right? If you now combine these two equations, and you can already notice that there is this nonlinear sign of delta showing up here, you can actually re-express the properties of this device as an inductor. But an inductor whose value has a constant, but it's now divided by this term cos delta, and delta depends on the current you are passing through the system, which means this inductance is not a constant, which is what you have for standard inductors. It doesn't depend, it's not independent of the current flowing through it. So that is where the nonlinearity comes from, okay? And this nonlinearity is of the same form of the nonlinearity, which is that of a pendulum as an oscillator, okay? Because now this is an inductor and a nonlinear inductor, I can use this instead of the linear inductor in my oscillator and build a nonlinear oscillator. You can also put two of these junctions in a loop, and then that allows you to tune the value of this inductance. This LJ0 is no longer a constant, but you can tune it with the help of a magnetic flux threading the loop. So for just a simplistic purpose of this talk, you can just think of Josephson junction squid as just a flux tunable, non-linear, and most importantly, non-dissipative inductor, right? The fundamental equations which describe the system actually tell you that this device cannot dissipate energy under normal operating conditions. So in fact, to the best of one, this is one of the most purest form of nonlinearity which doesn't come with any dissipation. Of course, that's not true in practice because this insulating barrier actually it's a dielectric, and that dielectric has losses. So even though at DC, which is basically zero frequency current and voltages, you might see the superconducting effect, which is in the sense of having no dissipation. At AC frequencies, you can have dissipations, and there are other effects which can prevent you from having this ideal behavior. But this is a very crucial component which is there in the superconducting quantum circuit toolbox, without which none of this would have been really possible. Okay, so now you have a nonlinear inductor, you replace the linear one and put a capacitor. Now I'm showing you typical values. This is 13 nanohenry. This is the value of that coefficient LJ0. Sort of the nonlinearity only kicks in at high excitations. So at very low excitation, it has a value of inductance around 13. Capacitance are usually in sort of 50 to 100 femtofarads. And this gives rise to a frequency of the oscillator, 1 over square root of LC in the microwave regime. So now instead of a parabolic potential, you have a cosine potential. And because of the nonlinearity, these levels are no longer equally spaced. Okay, so this is the parabola for comparison, and you can see that each higher level is slightly lower than the corresponding harmonic oscillator if we match the frequencies at low excitation. So this now allows you to create an anharmonic spectrum, just like the spectrum of, say, the electron's energy in a hydrogen atom or any other atom. You now have a nonlinear energy level structure. And because of that, you can now isolate the lowest two levels and make a two-level system. And now when you drive this in resonance with the lowest energy, which is approximately related to this LG and C, you will no longer excite the higher states. They're always present, but you will not excite them if you're careful on using your frequencies correctly. Okay. So this is how one builds a very simple qubit. This kind of a qubit it's one of the simplest qubits you can make, but it was not the first qubit to be discovered, and was given the name transmon. Okay. And it essentially operates at the same condition I mentioned to you, and that allows you to essentially be in the ground state. Okay. The real flexibility of this field really comes from the fact that you can really construct anything based on your imagination. You have at your disposal 3 building blocks: a capacitor, a Josephson junction, and a linear inductor. Right? So in the previous case, I replaced the linear inductor, but you are free to use it. For example, this would be a valid qubit circuit. And depending on what you choose and what parameters you choose, you will have some different potential well diagram. You will have different energy level structure. So you really have this enormous flexibility. It's almost like you're constructing your own Hamiltonian with the help of these things, designer Hamiltonian. And that's also why these qubits are often called artificial atoms, because it's like you're constructing your own atom by combining electrons and protons and neutrons in your own way. But here, the things you're combining are the Joule junctions, the inductors, and the capacitors, right? So this picture from this review article from 2013 shows you some of the devices, different types of circuits and their names, which are given here. And the Transmon, the one I just described, is the most popular. It's the design which is used in all the Google and the IBM processors you hear about, and even other companies. Though now this new device called Fluxonium, which is maybe about, I would say 8 years, maybe 10 years old, is really emerging as a possible alternative, but it's not there yet. And then in the past, there were other designs which were given up because these new designs improved on various aspects. And new designs are coming up all the time. I will mention one of our own work in this direction towards the end of the talk. Okay, so this might be a good place to...
Vijay, we can take some questions. There are a couple of questions. So maybe I'll read out. It's possible. Is it possible to get smaller and smaller superconducting circuit in future, or there are any limitations against it?
Okay, that's a very good question. The size of the superconducting circuit is somewhat related to the values we want to choose. Okay, so remember, these frequency values and temperatures values are sort of constrained by the technology we have. And it's also convenient frequency, because there's a lot of commercial electronics available in this frequency range, which is low cost and high quality, right? As opposed to needing lasers, which are sort of high costs and can be difficult to maintain depending on the kind of systems you're using. These are really off the shelf. In fact, there are circuits in your cell phone which create these kind of frequencies, or in your Wi-Fi routers, and what we use are not very different from that. And the motivation here is really not to miniaturize. So this is something we should keep in mind. That's not what we are trying to do. A quantum processor is not a smaller version of a classical processor where we have packed more transistors in a smaller volume. So that is never really the motivation here. No one is trying to miniaturize it necessarily right now. That's not the goal. If the first quantum computer is the entire size of the building, but it works, it's absolutely fine. With cloud access, one can run, and this is really more like a supercomputer kind of setup. So no one is really trying to make them smaller. In fact, you will see that some of the experiments people have been doing, including in our lab, are very big and bulky because they're really prototypes, and we are not really trying to miniaturize them. It is possible to really make them smaller and smaller. Remember, a capacitor is just a parallel plate. So if I want to keep the capacitance small, I could reduce the area and reduce the spacing. And in principle, you can make it smaller. Similarly, the Joule junction size can also be shrunk to be made smaller and smaller, but it makes the fabrication harder and could introduce other problems which are related to actually dissipation. The thing I mentioned that you have to minimize. In fact, about approximately 9 years ago or 10 years ago, there was a trend to actually make things bigger rather than smaller in superconducting circuits, because it turned out that making them bigger reduced the loss of the system. Okay.
The second question is from Rahul Bhaumik. Can you elaborate on how to get to commutation relation between Q and phi, the one that you showed before?
Well, I mean, there is really nothing much to elaborate. It's just that once you identify that the equations of motion are exactly the same form, but with the flux in place of the position and the charge in place of the momentum, then you just write it by comparison. There is no sort of, to the best of my knowledge, there's no hard derivation from root. Even when we write it down for position momentum, it's at some level it's kind of arbitrarily put in, at least the way it is taught typically. But it's really here, it's really just by looking at the form of the equation and then saying that, okay, it's the same thing, just a different physical quantity. So, you can write even in mechanical oscillators, you could have position and momentum, but you could have theta, for example. You could have angular position and angular momentum for a pendulum. Doesn't change things much.
So there is another question. How is a Josephson junction equivalent to inductor? Please explain.
Okay, maybe I can elaborate just a little bit on that. It really comes from these two equations. Okay, now these two equations are called the Josephson relationship. Basically, it tells you the relationship between current and the phase, and also the rate of change of phase and the voltage. So remember that if you now pass a DC current, which means I is constant, and it's important that this I has to be less than I naught, which is the critical current or the maximum super current the Josephson junction can support. If you increase the current beyond that, then it's no longer a Josephson junction. So that's a regime you should not operate in. So if I is constant, delta is constant. And if delta is constant, this term is zero, so the voltage is zero. So that is basically what a superconductor is. Current is passing, but there is no voltage drop across it. So hence no dissipation. Of course, this is only for DC current. For AC current, if delta is, if I is now varying as a function of time, delta will vary as a function of time, and then this is no longer zero. So there will be a voltage, but because this is proportional to the derivative, the current and the voltage are actually at 90-degree phase difference between the two. And that's essentially a property connected to the inductors, and that even in an ideal inductor, you don't have dissipation if there is no resistance in it, because current and voltage are always out of phase, like 90-degree out of phase with each other. So the same thing happens here. But if you really want to see where the expression for the inductance comes from, you just do this equation that voltage is equal to L di dt, right? So you can see this is proportional to the derivative of phase, which means it's also proportional to the derivative of the current. And you do that equation and write down V as L di dt, which is one of the expressions we know. It comes from d phi dt. And then by doing that equation, you can derive this expression. Okay, so that's it. That's how we know that it behaves like an inductor. It just means that the current phase relationship, or the relationship between current and voltage, is similar to that of the inductor, with the extra caveat that now it's nonlinear. See, if delta is always small, I can approximate cos delta as 1. And then the inductance has a constant value given by this h bar over 2e I naught. Okay. This is basically the value of the effective, the linear inductance. Just like a pendulum for small oscillations is a harmonic oscillator. Hope that's clear.
Okay, you can proceed. Yeah.
Okay, great. Yeah, those are great questions. Please keep them coming. So I stopped here. So there's lots of ways of building this. So we will look at some more circuits a little bit later today. Now we move on to the business of actually measuring this qubit, right? So till now I discussed this blue part of the circuit, which is the qubit. And here is a picture of actually the measurement architecture and how measurements are done in this system. So this circuit is really a circuit version of a well-known platform called cavity quantum electrodynamics, or cavity QED, which is essentially a cavity-based, cavity means a resonant cavity, based approach for studying light matter interaction. So normally, so that's the picture below. You have this Fabry-Perot mirror, system. You have two mirrors. One is partially transmitting. You can confine light in them, and you have a resonance. And then you can have an atom pass through it, which is sort of shown here schematically as a two-level system. And if this is resonant with the light inside, then it can exchange energy at the rate g. And the atom can also emit its energy at some rate gamma, which is related to its properties. And then the cavity itself has a decay rate of kappa, right? So these are the important elemental rates in a cavity QED system. This is the circuit version of that. Instead of the atom, we have the qubit, which is now a two-level system. Instead of the Fabry-Perot cavity, we now have a harmonic oscillator. So remember, the qubit is an anharmonic or a nonlinear oscillator. The measurement cavity, I will explain how the measurement aspect comes in just a little bit. This cavity is now a harmonic oscillator. And as some of you might know that, even the modes of the Fabry-Perot cavity near the frequencies can be described as a harmonic oscillator. So now you have a linear oscillator made with a linear inductor. And the two are just capacitively coupled to each other with these capacitors. And this capacitance here controls the exchange of energy between the qubit oscillator and the cavity oscillator. So that controls this rate G, which is the rate at which the energy is exchanged between the atom and the field, right? And then the oscillator itself is connected to your measurement lines, which in Fabry-Perot case could be free space or could be a fiber coupled to this field. In the case of microwave frequency circuits, this is just some wires which would go to a coaxial cable, which is typically used for sending and microwave frequency lines. And then this coupling, this capacitance, controls the rate of kappa. That controls the rate at which the cavity dissipates its energy into the environment. Okay, so this is essentially the circuit version of cavity QED, and has been also given the name circuit QED or circuit quantum electrodynamics, and was developed in the mid 2000s. And when you are operating in the regime where the qubits transition frequencies and the oscillators transition frequencies are off resonance, they're actually not on resonance. Typically, cavity QED is done in the resonant regime and is described by the Jaynes-Cumming Hamiltonian. But for measurement purposes, we actually don't want them to be resonant. And the reason is that we don't want the qubit to be exchanging energy with this cavity at all, because the qubit, it's doing its own thing. You want it to be able to preserve its state. So we keep it off resonant, and sufficiently off resonant given by this condition, that the difference between the frequency of the qubit and the cavity is much greater than the coupling strength of the two. And in this regime, the Jaynes-Cumming Hamiltonian can be written in this simplified form, where you have the qubit is the first term, which is written as a spin half, sigma z operator, because it's a two-level system, which is same as a spin half system. And then the oscillator term, which is written as this a dagger a plus half, which is the written in the ladder operator picture, has a frequency which was originally omega r, which is the bare frequency of this cavity, but it's now modified because of the presence of this coupling of the qubit, chi into sigma z. So this chi is a proportionality constant, which tells you how much does the frequency omega r change depending on whether sigma z is plus half or minus half, or is in the ground state or the excited state. So what you end up having now is a situation where the effective resonance of this cavity, this linear cavity, depends on the quantum state of this nonlinear oscillator or the qubit. Okay, and the difference is this value 2 chi. And chi is depends on the parameters of the problem, and it's basically related to this value of g and this value delta, as approximately goes as g square over delta. But there are some corrections depending on, because this is not a true two-level system, because the transmon really has higher levels as well. So it's somewhat smaller than the value g square over delta. So that picture that the cavity's resonant frequency depends on the state of the qubit allows you a physical mechanism to implement measurement. And what is that? You just measure the resonant frequency. Okay. So in practice, how is this implemented? So here is an example of a device from our group. This was not invented or anything, just showing you pictures. In fact, this version of putting a three-dimensional cavity, so this resonant cavity is now not even made as a LC circuit on chip, but instead it's made by just digging a hole inside a piece of copper and creating an electromagnetic cavity which has a resonant frequency. So it's sort of a different version of the Fabry-Perot cavity. So it really tells you that it doesn't matter how you construct it as long as it behaves like a harmonic oscillator. And in fact, you can see that this one is made out of copper, which is not even superconducting. And that's because the readout part of the cavity, we don't worry so much about the loss, because it's anyway coupled to the environment very strongly to be able to recover the signals from the system. Okay. So the chip here in the middle has the Joule junction shown here, and the the capacitors. And by just placing it here, in fact, we place it right in the middle where the field is the strongest. It's the antinode of the cavity mode. And this architecture was called 3D circuit quantum because the cavity was a three-dimensional object as opposed to a planar object on chip. Okay. And there were lots of advantages of doing this, as I mentioned once earlier, that the losses, you had also full control of the microwave environment, minimization of lossy, and at that time there was a big boost of coherence times from a few microseconds to about 100 microseconds or so. And this design is also modular, right? You can remove the chip, put a new one in if you like, and you'll see an example of this type of architecture at the end of the talk of something we are working on. The same thing, again, you're familiar in 2D. This is again a chip made in our lab. It's a 4-qubit processor design. This is really sort of an example chip. This particular chip never worked. So you can see there are 4 qubits here. Those are the capacitor pads you're seeing. In the middle, there's a Joule junction, which is not visible in this picture. And then now the microwave cavities are actually on chip. It's these meander lines. This is now the planar version of the true Fabry-Poro cavity. It's a section of transmission line with mirrors on both sides, where the mirrors are basically capacitors here, okay? And here's a sort of a picture of what it looks like. You can have your qubit here in red. These are the measurement resonators on one side, and then you have these other wire which connects the 2 qubit, and this is for the coupling. Remember, I mentioned that the qubits have to be coupled. So here the 4 qubits are also coupled to each other with the help of these lines. And these are also microwave cavities. So they are also used not only for carrying out measurements, they're also used for creating coupling for qubits which are far away from each other. The other common way of creating coupling is to just put the 2 qubits next to each other, and then that gives rise to some capacitive coupling between the two. Okay. So, and then, this can be scaled up, and you can have different kinds of chip. Here is an old chip of 9 qubits in a linear array. So here it's just by proximity. Each of this plus sign is a qubit. You see these squiggly lines, that is the measurement cavity. Each qubit has one, and they're arranged in a linear fashion. Here is a design from IBM, which 4 qubits, sort of similar to the one I showed you from our lab. Here's a 16-qubit design. And here's the Google's bristlecone processor chip, which has many, many more qubits in it. So you can put these together, right? So you've seen these pictures. But how does the measurement actually take place? So as I was saying, you have to measure the resonant frequency of this cavity, because that is what is going to tell you. And what we actually do is we map out what is the resonant response of the system with the qubit in the ground and the excited state. So here are 2 curves. The blue curve is the resonant response with the qubit in the ground state, and the red curve is the resonant response with the qubit in the excited state and shifted slightly. And what we are really looking at is actually the reflection phase. And the reason for that is, as constructed, these objects are perfectly lossless, right? So when you send in some energy to them, they don't absorb anything, they just reflect everything back. So in order to look at how the resonance is changing, you have to look at how the phase of this reflection is different as a function of frequency. So the resonant curves, rather than being some Lorentzian peaks or dips, they look like these this kind of phase response, okay? And then we don't actually have to sweep all the frequency. Once we know this mapping, then we can just operate at this middle point, and we drive the system with the microwave frequency at this value, omega d, shown here. And then we just have to look for a phase shift, because depending on whether the qubit is in the ground or the excited state, the value of the phase of the signal coming back is going to be different. And that's what you detect. And that then tells you that, okay, if the phase is some value, then this is ground state. If the phase is some other value, it's excited state, okay? And here is just a simple equation to show you what we are talking about, in terms of what goes on. This is just an oscillating signal with some phase, right? So just a sine omega t plus phi that can be broken up into sine omega t and cos omega t components. These are called quadratures. Then the coefficients a cos phi and a sine phi really contain the information about the amplitude and the phase of the signal. And these are called the quadrature amplitudes, I and Q. And often they are represented on an IQ plane like this. And a vector is now basically a way to tell you the value of the signal. The length of the vector tells you how strong the signal is. So that really depends on how much power you put in. And then the angle change tells you the phase shift, right? And the way I've drawn it sort of symmetrically about the I-axis, you can see that the projection of the red and the blue along the I-axis is identical. So that actually doesn't contain any information about the state of the qubit. It's only the Q-axis which contains the information of the qubit. These are just really details, because the detection system, which is called homodyne phase detection, really decomposes the signal into this I and Q, and then we just ignore the I values if it is sort of done, calibrated properly, and you can only look at the Q values, and that gives you the signal. Okay. So the signal is really shaped by the amount of phase shift. So you will see that if the phase shift is big, then it's a bigger signal. And then how much power you're actually using. So what is the amplitude of the signal? What is this A value? So the bigger the signal. So, and in the most fundamental case, the noise, there's in this measurement is actually set by 0-point fluctuations. In the ideal case, this is the fundamental limit imposed by quantum mechanics while you're trying to determine this thing, which tells you that, well, you cannot do better than this in a certain amount of time. So here in a sort of a cartoon way, we have shown these circles, which is sort of telling you the noise fuzzball of 0-point fluctuations, which is really the 0-point fluctuations of this harmonic oscillator cavity here at that low temperature. And if you're very careful with your experiments, it's actually possible to achieve that limit. Most standard techniques will never reach that limit, and you need special devices to do that. And that's what we will be discussing next. And the reason this is non-trivial to do, and I had mentioned this from the point of view of that measurement is not so easy, is that the typical power you use is very small. And the reason is the energy scale I mentioned, between the ground and the excited states is very small. And if you put too much power, then the whole, approximations break down, and things don't work anymore. And these powers are typically 1/10 of a femtowatt. You're talking about 10 minus 16 watts, very, very, very small signals. So you have to be amplified by a lot before they can be processed by conventional electronics, which typically need at least signals in the microwatt or milliwatt microwatt range to do things properly. And for that, you need very specialized amplifiers. And those amplifiers, some of them, while being commercial, the real important one is actually made in the lab, and that's called a parametric amplifier. Okay, so that's what the other superconducting circuit I'm going to discuss apart from the qubit. But maybe this is a point where I can pause again and take some questions if there are any.
No, there are no questions, so you can proceed in the chat box at least.
Okay, great. All right. So this is again a simplistic picture of what is a parametric amplification phenomena. And typically the picture is like this. You have some nonlinear medium, we can think in optical terms if you'd like, some crystal which has some nonlinearity, and you send two signals. One is the signal you're actually trying to amplify, and the other one is a very, very strong, much, much stronger. I mean, here this is just a cartoon version, but typically this would be 10,000 times larger in power than this one. And the role of this very large signal, which is called the pump, is to really activate the nonlinearity in this medium. And when it's activated to the right level, then this very small signal actually interacts with this pump because of the nonlinearity. And at the output, you now get an amplified version of the signal. The pump comes out more or less the same because it's much, much bigger. So the change is very small. And then you also get this other copy of the signal called the idler. And, energy conservation says that you have these two kind of processes. One is called 3-wave mixing, this one, where you have omega pump equals omega signal plus omega idler, or you can have 4-wave mixing. That really depends on the type of nonlinearity you have here, which gives you 2 omega pump equals omega signal plus omega idler. Okay. And this kind of phenomena can be implemented using nonlinear superconducting circuits. And what do we use for the nonlinearity? It's the same Joule junction. Okay. The generic picture of how to do it with this kind of physics with resonators is this idea that if you have some kind of a Fabry-Perot cavity, like I mentioned, you have one reflecting mirror, one partially transmitting mirror with a natural frequency of omega naught. If you could modulate the resonant frequency, say by moving this mirror back and forth, but at a frequency 2 omega naught, so twice the natural frequency, then the same physics happens, which is that if you send a signal in close to resonance, which is omega naught, then that signal interacts with this pump and then gives you an amplified copy of this signal. This is an alternate version of the nonlinearity, the nonlinear picture I presented in the previous slide. And this can now be done in circuit form by using a squid as a tunable inductor as part of a resonance circuit, and then applying a magnetic flux to change the resonance frequency at a very fast rate, right? So remember, the inductance could be tuned with the flux if you put two of them in a loop. So if you now apply a oscillating magnetic flux, that inductance will change the overall resonant frequency at the same rate, and you get the same kind of effect. And these kind of circuits were built. Turns out again, there's a something closer to the first picture, is if you just build a nonlinear oscillator. Now look at this circuit. This looks exactly like the transmon circuit, but the difference is in the values of the inductors. Now the inductance is much smaller. There it was 13 nanohenry. This is about 0.1 nanohenry. So it's about 100 times smaller. The capacitance was about 70 femtofarads, and this is 6 picofarads. So it's about 100 times bigger. What that means is that if you now look at the potential diagram, there are now many levels, than compared to the transmon circuit. So this is more in the semi-classical regime, and it's also driven to a much higher level of excitation. We are not using this as a two-level system. We're just using it as a nonlinear electrical oscillator. And here's a picture of such a device here. So there is the squid, and here are the capacitors. This shaded in green. There are two plates, and they are separated by an oxide, which gives you the dielectric. Okay, and such a nonlinear system has this kind of a response. So this is what it's showing you is the response of the oscillator, which is measured by this delta. You can think of delta as the oscillation amplitude as a function of the frequency of excitation, from low powers to high powers as a function of its colors. So at low powers, you get the familiar resonance, like a Lorentzian shape. But as the power is increased, these curves start to bend towards the left, towards the lower frequency. And this is all happening because of the nonlinearity of the system. So this is actually a very well-known, very old nonlinear classical physics, the physics of the Duffing oscillator, or the driven Duffing oscillator. But you can see that beyond certain power, the system actually is multi-valued. Like for a given power and frequency, you can actually have different responses. You can have a high response, you can have a low response. And from the point of view of amplification, our interest is actually in these curves, which are closer to a power shown by this red curve or this green curve, where there's this very sharp change here, almost like an infinite slope here. And this is the point where the nonlinearity gets activated, like the way I had mentioned. So you have to choose the power correctly so that you're operating here. This is just the phase response of the same oscillations here. When you do that, when you go and bias at this point, this parametric amplification phenomena of mixing of these signals takes place, and you get an amplifier. Okay, there are other versions. I'm just showing you this. I'm not going to discuss this in detail as the examples of the variety of things you can do. Again, because of the flexibility you have, this is a lot more complicated circuit with 4 junctions in a loop. And this was, again, a new amplifier design which was developed. Now the signaler and idler modes are actually specifically defined as different oscillators here. But I'll come back to this circuit because one of our qubit works is related to this 4-junction system, and you will see that in the later half. But this was another design of building these nonlinearity-based parametric amplifiers. And even though I'm not going to discuss in detail, it's important to mention that these amplifiers allow you to really amplify the signal without contaminating them with additional noise. In fact, it turns out that quantum mechanics places a limit on how well you can amplify. It says that there always has to be a minimum noise which has to be added. Most of the amplifiers which we use in daily life, whether they are audio amplifiers or microwave amplifiers they are far from that limit. And this limit is called the quantum limit of amplification. And these devices operating at low temperatures with these non-dissipative components carefully designed can reach that limit, which means these are some of the world's best amplifiers which can be used for these experiments. And they're very crucial for achieving the results which people have done today. Okay. Now, how are these things put together? So here's an example of the wiring of the fridge. This is sort of something similar to what we have in our experiments. And this is the cryogenic part of the wiring. So which is what is inside the dilution refrigerator. You typically have lots of attenuators for the signal coming in. So look at the first, it's called labeled line N4. This is where the input signal comes in for, say, manipulating the qubit state or measuring the qubit state. And you have to typically go through many attenuators. And these attenuators suppress all the noise which is coming from the room temperature. Because remember that your device is at very, very low temperatures, cannot handle signals which are very big. So if you just connect it directly, just the fact that you're sitting at room temperature, your components are radiating Johnson noise at that temperature. And that can just come down and completely ruin the effect of being at those low temperatures. So these attenuators actually kill all of that noise and bring it to a low level, but they're also killing the signal you're sending in, but that's okay because you can just increase the value of the signal, like increase its amplitude so that it's sufficient. But by the time, even after all this attenuation, each one of these attenuates it by a factor of 100. So by the time you're here, it's 10 to the power 6. And then there are lots of filters, and then the signal is routed to the device, and then it interacts with the device with the cavity, and then it comes back out, and it's routed to this second device. This is the parametric amplifier, and then it's routed back out where it's amplified by more commercial cryogenic and regular amplifiers before going to the signal. Okay, so this is just really to tell you also the complexity of these experiments. Lots of filtering, shielding, cryogenic amplification are needed to really ensure that the device is in the quietest possible environment with minimal disturbance from the outside, and also that you recover the signal with the highest signal to noise ratio by using these specialized amplifiers, which we also build in the lab. Okay. So once you are able to do this, what is the kind of effects you can see? So here's it again, your qubit inside this cavity. Here's a picture of one of these amplifiers made out of, again, nonlinear oscillators in our lab. And then you can really get fantastic data like this. Now, let me just walk you through what you're observing here. There are 6 curves, in different colors. Each of these is an identical experiment, just repeated 6 times. The y-axis is basically the phase shift of the measurement signal which I measured, in terms of some arbitrary units, which is the detector, which is converting the phase into some value, into some digital value. And this is time. Okay, so the experiment involves by putting the qubit first in the excited state and then starting to measure. What you're seeing, let's take this blue curve here in the middle, is that the labels tell you that this level corresponds to state 1 and that level corresponds to state 2. So note that all of them, the experiments are identical. They all start with the qubit in the excited state. So they all give you the same value here. And then as a function of time, you see this transition from the excited state to the ground state. Each of those curves show the same effect, but it's happening at different times. This time is completely random. This is just 6 sample experiments. But each curve is a single experiment with no averaging. It's a real-time continuous observation of the quantum state. And what you're seeing are really the transition of the qubit from its excited state to the ground state in real time. Okay. So this is really giving you an indication of the quality of the signal. There's no ambiguity in distinguishing between the 2 states. You can see the transition. The transition is, of course, random because you cannot predict when that decay happens, as you expect for. And this is basically the spontaneous emission of the qubit from its excited state to the ground state. And these kind of measurements are only possible with the help of these kind of amplifiers. Though some newer designs, including in our own lab, we have been able to see this without the use of these specialized amplifiers. But maybe I can explain if somebody is interested in how we did that. So this really is these are called quantum jumps. And this was one of the main experiments which was done in the 80s, but on the ion trap system, which ultimately led to the Nobel Prize in 2012. And in the superconducting qubit system, I was lucky to do this experiment during my postdoctoral days, where we had developed the first version of these amplifiers in 2011, and that was published in this PRL. This data is from one of the experiments we did in our group in a multi-qubit system, just to show you the quality of data. Okay. These kind of measurements are often called strong measurements. I know that some people in ISO Kolkata have interest in quantum measurements, so I thought I will say something about that here. And strong measurements is just another word for the textbook measurements you learn in your intro quantum, which is basically projective quantum measurements. So here the system is projected into the excited state. Here the system is projected into the ground state. Of course, this projection here, the transition is happening because of some other basically spontaneous emission. But if you had started the system in a superposition, it will either project to the ground or the excited state with the probability given by the kind of superposition you actually created. Okay, but it's also possible to do weak measurements, which are actually partial measurements, and that can be done very simply by just making your measurement tone weaker. Okay, so this is the typical pulse protocol. You put a pulse to the qubit to prepare it in the excited state, and then you send a pulse to the cavity to make the measurement. So for a strong measurement, you just use a larger amplitude. And why is that relevant? Because a larger amplitude essentially gives you more signal to noise ratio. In a given time, you can resolve the two states. And a weak measurement in this picture is just a signal which is just not strong enough to resolve the state. Okay, it's not because of noise which is masking. There is noise always there, which is the 0-point fluctuations. It's just that your signal is not strong enough to extract. And that directly translates to the fact that you're not projecting the system. Okay, so since I'm running a little low on time, I'm not going to elaborate on this, but it's possible by just controlling the power and looking at the response to really see what happens in the weak measurement. And you can observe these kind of quantum trajectories. So what you're seeing here is that again, identical experiments, multiple runs, but this time the qubit was initially prepared in the equal superposition state. So that's why the initial probability, which is plotted here, which is the probability of being in the ground state, is 0.5. Okay, and then as time evolves, you see the system sort of doing this random walk either towards the ground state or towards the excited state. And if you repeat it many times, you will see that approximately 50% of the trajectories will end in the ground state and 50% will end in the excited state, as should be the case for an equal superposition state. So what you're really observing here, look at the time scale here, right? This is now tens of microseconds, as opposed to the time scale here to go from ground to the excited to the ground state. So here this is just the response time of the detector. It's basically instantaneous. Here, what we have done, because of the weak measurement, we have slowed the projection. So the qubit slowly is evolving from its superposition state and then getting projected. And once it's projected, it sort of stays there. That's again a feature of quantum mechanics, measurements in quantum mechanics, that's what should happen. And you're just seeing this happen at different time scale, because this is again a purely stochastic process. There's no fixed time at which it will happen. There's a characteristic time scale over which these projections will take place. And that characteristic time scale depends on how strong this measurement is. The weaker the measurement, the longer it will take to project. It basically, the projection time is the amount of time it will take to get enough signal to noise ratio that you are now able to resolve the state. So there's a very nice connection here in this, and this experimental setup allows you to see this connection between the fundamental availability of information and the projection of the quantum state. By reducing the signal, we are limiting the rate at which we are acquiring information. It's not because of some technical noise that we are not able to do it. Fundamentally, there is no information available because we are carefully controlling that. Okay, so these experiments were done first at UC Berkeley and at Yale, and there were some very nice papers. This data on the left is from our group more recently, but these kind of experiments are possible in this thing. So the goal here is to highlight that apart from applications in quantum computing and other things, you can also do fundamental experiments involving quantum measurements and things like that in these systems. The quality of the measurements and the control is good enough to be able to test some of these ideas. Okay, so let me pause again here before I go to the last part and see if there is any questions.
There are a couple of questions. So one is, what is the explicit form of the Hamiltonian of nonlinear oscillator?
It's basically the harmonic oscillator. So remember that if you have a harmonic oscillator, you have a term which is like p square over 2m and then say x square, term proportional to x square. So the term proportional to x square is basically the term which is related to the displacement, right? So instead of that, you will have a term like cos x. And that cos x is basically comes from the nonlinearity. And remember that if you expand cos x to the leading order, it will give you x squared. So that's the harmonic approximation. I guess I don't have a slide here where I have written down the explicit form. I have approximated to the two-level model, but essentially there'll be a term proportional to cos of delta in the Hamiltonian instead of
this cos delta term they can see in standard textbooks on superconductivity, like
absolutely. Or you just look up any paper on the Transmon Hamiltonian, you will see. Here I just wrote the simplified version, but that's all there is to it. In fact, you will see a version of this Hamiltonian just in a second. I just remembered there's going to be a slide, so you will see that.
So there another question: what is the use of the copy signal idler?
There's no use per se. I mean, there are some cases where you can use it. It's just that the physics of the nonlinear process demands that this additional copy is created. It comes from the conservation of energy of the pump and the signal photon, that there is a second frequency which is created because of the interaction of the pump and the signal. The idler copy is usually just ignored. It has identical information as the signal copy. So it, in some cases, because the frequency of that signal is different, if I go to, there are some circuits like this one I had shown, there the signal and the idler actually come out of two different physical ports. Whereas here, there's only one port and the signal and idler come out of the same port, just different in frequency. So in these kind of setups, the idler can be used for some interference experiments and things like that. But from the point of view of amplification, if for some reason you prefer to operate at the idler frequency rather than the signal frequency, then you can use that. But it has the same information as the signal. So in that sense, it's not really.
Well, there is another question which I think you have already answered before, that what exactly makes this platform eminent among other quantum computing platforms? So you had already compared the different platforms once at the beginning.
Well, okay. I mean, I sort of compared it, but I didn't necessarily say why one is better. There are a few points. I'll just take a minute to say there are actually several reasons. And I did mention some of them, though not in this context. The ease of operation plays a big role in the success, especially in the early days of building it. Now, with the superconducting qubits, when compared to trapped ions, in the beginning, the superconducting qubits had too much dissipation. So, the coherence times are very small. Today, the coherence times are typically in the 100 or hundreds of microsecond range. But when they the first experiment in 1999, that time scale was 5 nanoseconds. So, we have had 6 to 7 orders of magnitude of improvement already there. But the real importance, from the point of decoherence is the metric, which is you have to consider is not just the decoherence time, but it's the ratio of the decoherence time to the time it takes to do a single operation, which are these gates, because that tells you how many gates you can do before something bad happens. And bad here is just a random process which is happening because of decoherence. Remember, a quantum algorithm or these gates are carrying out deterministic operations on the change of your state of your qubit, whereas the decoherence is inducing random operations on the state of your qubit. And it's basically a fight between the two. So in superconducting qubits, this ratio is very favorable. Even though the decoherence time is low, you can do the manipulations very, very fast. So somewhere in the 10 to 100 nanosecond range. Whereas in trapped ions, the decoherence times are much longer, in milliseconds and longer, but they're also slower. Their gates typically take microseconds to do. And this is actually quite fundamental to most platforms. And this has to do with the fact that you have to protect the system from the environment in order for it to have long coherence time. But if you protect it too much, you can't even get your signals in properly. So this is a balance which has to be struck. And then this fact that microwave frequencies are commercial technologies, easily available, they are stable, unlike lasers, which are somewhat trickier to operate. All of these sort of made superconducting qubits actually come up very quickly. It was really the rapid rise. I would say that today superconducting qubits and trapped ions are roughly neck to neck. In fact, with some recent results, I would even say that trapped ions have just edged a little bit ahead. And if I repeat the salesman pitch of the ion trap people, they really say that their quantum qubit is perfect because the decoherences are very small and it's absolutely perfect. They really have to figure out the control electronics, and that's a classical problem, an engineering problem. Whereas with superconducting qubits, the qubit itself is not just yet perfect. So we are not there yet. And some ion trap people think that it might be very difficult to improve the coherence beyond a certain time. But we don't necessarily believe. There's still been progress. We are now approaching milliseconds. So there are some obvious concepts and some sort of subtle things which have really led to the success. But as I said, this is not the end game. I mean, tomorrow there could be a new platform. Semiconductor-based quantum dots are really coming up in a big way. Photons are back in a big way. One of the big challenges with photons was they don't like to interact with each other, which is why it makes them great as qubits, because the coherence is practically non-existent. But because of the same reason, they don't interact with anything, so you can't do gates that easily. So this is really the balance, and all of the different platforms have different pros and cons. So
okay, you can proceed.
Yeah.
So you have about 15 minutes left.
Excellent. Okay. So basically, in the last part, I want to give you some examples of the work we are doing in our lab. And the first one is really a completely redesign or different way of thinking about a multi-qubit circuit. Right? So remember that the single qubit transmon was a single nonlinear oscillator. It had one mode, it had one inductor and one capacitor, and that created one mode of oscillation. So we made this circuit, and remember I showed you this kind of a circuit with 4 Joule junctions. Earlier it was in the context of the amplifiers. Here it's again, and the difference is the same. The value of the inductance and the capacitance are in a different regime. But this circuit, which has 4 Joule junctions and capacitance as shown. So here's a picture of that. So there is this squid loop now has 4 junctions. So 1, 2, 3, 4. And there are these 4 pads now, okay? And each pad has a capacitance to the other pad. And that's what sort of explicitly shown in this diagram. If you analyze this circuit, this is like a more complicated mass spring system with more masses and more springs. So it has more than one normal mode of oscillation. So this particular circuit has 3 finite normal modes of oscillations. So normal modes at finite frequencies. And because it's all coming from the same single circuit, because of the nonlinearity, they actually behave like 3 coupled anharmonic oscillators. So it's now a single circuit, which is more complicated, at least in design, but in terms of fabrication, it is just trivially more complicated. But this now has 3 frequencies at which it can become resonant, okay? And essentially, those 3 frequencies can now be used as 3 qubits. So this is straight away a 3 qubit system. So this was developed in our lab a few years back, and we called it TriMon, tri for 3, and mon from the same transmon because it's the same type of qubit. It's again a nonlinear oscillator-based qubits. And these normal modes are really simple to visualize. They're basically, just sort of the normal modes of this circuit. So one mode is, an oscillating, in this direction with these 2 potential being at 0. The second normal mode is 90-degree version rotated of that. And the third one is, if you call it a quadrupolar mode, because it has this 2 plus and 2 minus. So these 2 are at same potential, and they oscillate with respect to these 2, which are at the same potential. And these have different symmetries, and that gives rise to some interesting possibilities. But in terms of just the 3 modes, these are how one can think about it. You can really think of this as you can actually look at what's going on. If you think of this as a discrete string, with a periodic boundary conditions, and then that way you can actually solve. So if you look at our paper, it sort of goes into the detail about, there are a series of papers actually about details of how to compute these normal modes. And then in order to write the Hamiltonian, and this is where you will see the explicit nonlinear term, you have to compute it in terms of the normal coordinates, right? Just when you go to the normal mode frame, you have different coordinates. And so now instead of these fluxes phi 1, phi 2, phi 3, and phi 4, which are what's called node fluxes, which is basically just the integral of voltage with respect to time, you now define new coordinates phi A, phi B, and phi C, which are defined in this form. And then in this picture, you get the Hamiltonian of this particular ring, which is just the Joule junction, as a product of cosines. Okay, so if this was just a single mode, there will be only one cosine here. So you have EJ cos phi A, cos phi B, cos phi C, and cos phi. Phi is the flux in the loop. But usually we operate with zero flux in this loop. And so this term just goes away because this has a sine of phi, and this is what you're left with. Okay, and then we expand this to the lowest nonlinear order. So you now add the capacitance part. So this is the Hamiltonian of the trimon. If this was the transmon, you just basically remove the terms in phi B and phi C, and then that would be the explicit nonlinear Hamiltonian for the transmon, right? And then we expand the cos phi to the first nonlinear term, because that's sort of a good approximation for these type of qubits. And this is now like a transmon-like qubit. And similarly, you have for B and for mode C. So you have 3 qubits. And the most important thing is that you have now terms like this, which is phi A square, phi B square, phi B square into phi C, and phi C into phi A. This is now the coupling term. And these are called cross-Kerr coupling terms, because what they do is if you excite one of the modes, it changes the frequency of the other 2 modes. This is the coupling interaction. This tells you that the state of one qubit affects the state of the other qubits. And that is how you can really think of this as a coupled 3-qubit system. And really, you have to imagine this. And this is now writing the Hamiltonian in terms of sigma z's. So specializing it to 2 levels. This is at the Duffing oscillator level. This is now at the 2-level approximation. And now the coupling term looks like sigma z. Okay. So to really think about this, you have to consider this as just an 8-level Hilbert space, where these 8 eigenstates are composed of the 2 lowest eigenstates of each of the modes. And they're just labeled by, the qubit states, so 001, 0, 001, 010, 10, and then more and 4. And they're connected by these transitions, which tells you that you have to apply a frequency of that value to excite a transition between here and here. Okay? And this basically means that in order to achieve full universal manipulation of this 3-qubit Hilbert space, we just need to address these 12 frequencies, which are sort of shown in sets of 3 colors. There's blue colors, red colors, and green colors, which are notionally associated to the 3 different qubits. But because they're actually coupled, each qubit really loses its individual identity. For example, this transition, which takes the red from 0 to 1, cannot be thought of as the red qubit, because this is the transition when the other 2 qubits are in 0, 0. The next red transition is also a transition on the red qubit, but with the other 2 qubits on 1, 0, and so on and so forth. So they're inherently coupled, and you cannot really separate them. But for the purposes of logic gates and all, you can define them. And then that's all you need. And then, this elementary operation no longer implements a single qubit gate, but it's actually a 3-qubit gate, because it depends on the state of the other qubit. It actually implements a control knot, which is also called a Toffoli gate. And that really gives a lot of power. You can now combine the control knots, 2 control knots, CC knots, to create a control knot, or 4 of them to create a single qubit rotation. So here the complexity is reversed. The 3-qubit gate is the simplest, and the single qubit gate is the most complicated. So that has some pros and cons. But we were able to use this to implement the Grover's algorithm, one step of that. And the oracle is shown here. You first prepare it in the equal superposition state, then the oracle does the sign flip and the amplification. And what we were able to show is that because of this inherent coupled nature, some of these gates were very, very simple and short in time, because of which we were able to implement it with much higher quality. In a single Grover iteration for a 3-qubit system, you should only get the correct answer with 78% probability. And we checked it for all the different possible states, and we got somewhere between 40 and 55%. So we didn't reach the theoretical limit because of decoherence, but it was fairly good. And when we actually compared it with the best available data in literature at that time, so this is now already a few years old, which was actually on a trapped ion system. And there, the average success was about, significantly lower than what we were able to show. We had 49% in comparison to the ideal 78%, and they had only 39%. And this is because the gates which were required in the Grover's algorithm were a lot more complicated to implement in the trap-down system as opposed to our system. We also ran it on the best IBM qubits we could find, in their online system. This was last year, and that reached about 45%. So we were doing somewhat better than them as well. Even though their qubits are a lot more coherent, our gates were a lot more efficient because of this new model. Now, of course, this doesn't mean that this would be better for every algorithm. That is something we are working on. That what are the advantages, and we're trying to use these trimons now as building blocks to build larger qubit networks. Okay. So just one last thing I wanted to mention is about, this is our latest project in our group, and it's got to do with how qubits are connected. So this is a typical 2D layout of a qubit chip. The red dots are the qubits, and then these squiggly lines are the connections between them. So these connections are what determine whether you can do a gate between, say, qubit number 4 and qubit number 5. So 4 it's easy to do a gate with 12, and 5 because they're directly connected, but it's not easy to do a gate with 13 because there's no direct connection. You have to go via this. So similarly, to do a gate operation between 4 and say qubit 16, you cannot do a direct gate. You have to do many intermediate steps, which means more steps, which means more time as compared to the decoherence, so which means more errors. So this is a typical challenge in any qubit layout. Like, how do we create a system where you can do gates between distant qubits? Okay, so for this, we actually developed a new architecture. And this architecture actually, instead of having individual connections, we actually have this circular path here, and the qubits are all connected to that path. So now the blue dots are the qubit, and this circular path is basically a long section of transmission line which closes on itself. And what we were able to show is that by putting qubits uniformly around this at some 30-degree spacing and choosing the operating frequency correctly, we were able to create a network of connections like this. So even though there is no physical direct connection like this, the fact that there is a path which always exists allows you to create these. So these solid lines here are showing you the effective connections. They are not actual, there's no wire going from here to here directly. And what we showed is that in this 12 qubit network, each qubit is connected to 9 other qubits, as opposed to here where each qubit might be connected to only 4 other nearest neighbors qubits. And then if you look at the paper which is on the archive, we have shown extensions of how this can be scaled up to larger and larger qubits with more rings and things like that. So we're really excited about this prospect where you can connect to more qubits, and this will allow you to do more efficient gates by less number of steps. And we are working on those experiments. So here's actually the image of this experiment. Again, we did it in the 3D architecture where the cavity, the readout cavities are these little spokes here, designed and machined in aluminum. And the central ring you can see here is this big circle. That's the coupling bus. And then the qubits are all placed like this across the individual chips. So this is the modular architecture I was mentioning for the 3D design. This was just easier for us to do as opposed to designing a 2D full chip, because we don't fully have that setup in our institute, but we are working on that. But here you can remove the qubit if it's bad, put a new one. It's quite easy. And this the rest of the stuff is actually machined on a CNC machine in a workshop. Okay, so with that, I'm going to wrap up and just summarize what we discussed. That we know that computing with quantum bits can provide tremendous power, and I introduced the superconducting circuits, and they are a very strong candidate for building, say, the first practical. And even though a lot of things have happened, I really want to emphasize this point that this is really just the beginning. There's a lot of work that needs to be done in terms of getting these to work. And it's really an interdisciplinary effort. You need physicists, computer scientists, engineers, biologists, chemists, industry, because there are lots of applications which we have to develop together. And as some of Google recently did this experiment a little over a year ago, which demonstrated the quantum advantage, which is that it showed for the first time that some problem which is very hard for a classical computer was solved much more efficiently on a quantum computer. Okay, so thank you for your attention, and I'll take any last questions.
Thank you, Vijay. Thanks very much for a wonderful talk, which I'm sure that the students found very, very useful. So, okay, so there was one question which was probably more personal. If somebody wants to join your lab, what are the skills required and how regularly do you? I think that the person can directly get in touch with you, right? So one of the things is they have to clear the TIFR interview process. So that is one thing. Another question is how, so in the 12 qubit network, if you are able to connect all the qubits, then what are the error sources or any difficulty in connecting two qubits?
So in our current design, all the qubits are not connected. As I said, that every particular qubit is only connected to 9 others. So if you take Q1, it is not connected to Q5 and Q9. So basically, the in relative angular positions, 120 degrees from it, those are the 2 qubits which are not connected. All the other 9 qubits, it has connections. So what does connection mean here? It means that a physical interaction exists between this location and that location. And that means that I can now implement a quantum gate between those two directly. As opposed to this layout, where these squiggly lines represent the direct electrical connection, which means a direct gate is possible between 4 and 5, but not between 4 and 6. But it doesn't mean that you cannot do a gate between 4 and 6. It just means that that gate will have to be decomposed into sets of gates between 4 and 5 and then 5 and 6. So it means more number of steps. So it would be simply solved if you were able to put wires from, wires within codes. So here you have to do it correctly. If you could put wires between every qubit and every other qubit, but then that is a gigantic mess. How do we do it in a practical fashion? So there are probably many ways of doing this. So this is sort of one of our ideas, that having this kind of a circular, it's really circle is just the convenient shape. It's just something with the periodic boundary condition, allows you to solve this without having to create all the extra wires. So right, we are not, so Q1 doesn't have 1, 2, 3, 4, 9 wires connecting it to the 9 qubits. It's just part of this common shared system. And what we really showed is that how to use this kind of a system correctly in terms of what is the correct choice of frequencies, how should the qubit be spaced so that the coupling strengths, if you notice, there are 2 colors here. There's a dark blue color and a light blue color, and they represent 2 different coupling values, which means that the interaction for certain qubits is stronger and for certain qubits it's weaker. And it's about a factor of √2, in coupling strength. And that determines gate speed. So those things are also important. You just cannot, you might think that, oh, this looks like a circular symmetry, so let me just put lots of qubits here. It doesn't work. Only for special angles it works, and that's what we were able to show. So the challenges beyond that are just that how do you do the gates? Here the coupling is always on, so that also introduces challenges on the certain kinds of qubits. So we have suggested that for future, we really need some kind of tunability, where the coupling of the qubit to this bus network, this cavity, which we call the ring cavity itself, can be controlled with another knob. And then that way you can control the overall interaction. Okay. Otherwise, too many qubits interacting at the same time is also a problem that can give rise to errors.
Okay, Vijay, thanks. So we have already run out of time. So maybe we'll take one last question.
Okay.
So which is like, how does entanglement work in these qubits?
Okay, I'm not sure what exactly you mean, but if you're asking how does one create entanglement between these in these qubits, is just the fact that there are these physical interactions. By applying the right kind of microwave signals to the relevant qubits, let's say if you want to entangle 4 and 5, you have to do a specific sequence of operations. In terms of a quantum gate, it could be a 2-qubit gate like a control knot, and that can create an entangled state between the two. But there are other kinds of entangling gates which are possible. It depends really on which protocol you use. And then by applying those signals, you create the right type of 2-qubit evolution, which causes the initial independent or separable state to evolve into an entangled state. So that's essentially, you have to apply the right gates. And this can only be done with the help of these 2-qubit gates. That is when the qubits are interacting. Yeah. By just locally controlling the qubits by single qubit gates, you cannot create entanglement. So that's why this physical interaction is very important.
Yeah, you have already showed one control knot gate earlier in the talk. So that was a entangling gate.
Yeah, so that's there's a little bit of subtlety here. When you have an 8-level system, I mean, it is possible to create a state like, say, 0, 0, 0 plus 1, 1, 1. But whether you would call that an entangled state is a subtle question. It depends on how you view it.
Right.
Because this is really an 8-level system. There are no separate physical objects. Typically, the entanglement is used to describe objects which are physically distinct. And this is something actually we have been also pondering our head over, because even though we can map this to the same standard language, the same ideas don't exactly translate. So, and the reason for that is that these 3 different modes, which represent 3 qubits, are not 3 different physical objects. They are normal modes. They are of this circuit. So it's a single object. So then, what does it mean to have a one normal mode entangled with another normal mode? We are not really sure exactly how to think, but this is a special case. But in a more general cases, the entangled states are defined in the conventional fashion, and you need to use multi-qubit gates to do that.
Right.
Yeah.
Okay, Vijay, thank you very much. I'm sure everybody enjoyed the talk, and thank you. And if any